Okay, let's look at the in-class worksheet here on continuity. Number 1, find the intervals on which each function is continuous. So here we have f of x is equal to x squared plus 2x plus 1 if x is less than 1, or negative x over 2 if x is greater than or equal to 1. So we have a piecewise function, and we can tell that there is a break in the graph here. So it looks like it's not going to be continuous at 1 here. So we have from -1 to +1, and then from 1 to infinity. So negative infinity to 1, and then from 1 to infinity. All right, find the intervals on which each function here is continuous. F of x is equal to 1 at x and not equal to 5, or f of x equal to 3 at x equals 5. Or you can see right here at x equals 5, we have a hole in the graph, and it would not be continuous there. So from negative infinity to 5, and then from 5 to infinity. All right, find the intervals on which the function is continuous. You use the provided graph to sketch the function. Well, f of x equals 2x minus 10 if x is less than 2. That's going to look something like this. Now, f of x equals 0 if x is greater than or equal to 2. You can see that that is right along the x-axis there. So, from negative infinity to 2 is one continuous section, up to but not including, and then from 2 to positive infinity. And up here again, for number 1, that was from negative infinity to 1, but not including it, and then from 1, including it, to positive infinity. Let's take a look at this one. X squared minus x minus 2 divided by x plus 1. Well, that turns out to be a straight line, but we have to consider that at x equals -1, there's a hole in the graph. So from negative infinity to -1, and then from -1 to infinity, not including -1 either place. It's discontinuous there. All right, find the intervals on which the function is continuous. So we don't need to graph these. We could if we wanted to, but let's take a look. F of x equals x squared divided by 2x plus 4. Well, f of -2 would tell me that I have 4 over 0, so it would not be continuous. There'd be a hole in the graph there. So negative infinity to -2, and then from -2 to positive infinity. Let's take a look at this piecewise function. F of x equals negative x over 2 minus 7 halves, or if x is less than or equal to 0. If x is greater than 0, then negative x squared plus 2x minus 2. Well, let's take a look at what happens right at 0, at the transition. F of 0 is equal to negative 7 halves. So the limit as x approaches 0 from the left-hand side is negative 7 halves. But the limit as x approaches 0 from the positive side, or the right-hand side, is equal to -2. So there is no continuity at 0. So from negative infinity to 0, and then from 0 to positive infinity. All right, let's look at this one. 7. F of x is equal to negative x squared minus x minus 12 all over x plus 3. Well, f of -3 would give me a 0 denominator, and also give me a 0 numerator as well. So 0 over 0 tells me that there's going to be a hole in the graph there. So negative infinity to -3, and then from -3 to positive infinity. All right, f of x is equal to x squared minus x minus 6 all over x plus 2. F of -2 is equal to 0 over 0. So again, at -2, we're going to have an asymptote, and there is not going to be continuity there. So negative infinity to -2, and then -2 to positive infinity. All right, let's look at number 9. Determine if each function is continuous. If the function is not continuous, find the x-axis location of and classify each discontinuity. So f of x is equal to negative x squared over 2x plus 4. I can tell that x equals negative 2, I'm going to have a 0 denominator, and that's going to be 4 over 0. Well, since we have a number over 0, that's going to be an infinite discontinuity at x equals negative 2. They have used the word essential. In our notes, we use the word infinite. Number 10, f of x equals x plus 1 over x squared minus x minus 2. Well, we could factor that. And if I look at that, f of negative 1 would be 0 over 0. So that would be they use a removable discontinuity there. And f of 2 is equal to 3 over 0. So that would be an infinite discontinuity at x equals 2. All right, let's take a look at here. X plus 1 all over x squared plus 1 plus 1. Well, that would be a continuous function because there is no place where I could, no real number that would make this a 0 denominator. So it would be continuous. Number 12, f of x equals negative x squared divided by x minus 1. Well, I can tell at 1, I'm going to have a 0 denominator. So f of 1 is equal to negative 1 over 0. Well, that's going to be an infinite discontinuity at x equals 1. Let's look at number 13. X squared minus 4x plus 3. If x is not equal to 0, or f of x equals 3 at x equals 0. Well, let's take a look at the transition point at x equals 0. F of 0 equals 3. The limit as x approaches f of x from the left-hand side, 0, would be 3 as well. And as we approach from the right-hand side would be 3. So this would be a continuous function because this, okay, would actually be fill in the gap here for this function. All right, f of x equals negative x squared if x is not equal to 1, or 0 if x is equal to 1. Well, let's see what happens at the transition point. F of 1 equals 0. Well, what happens as we approach on this function? F of x, as a limit of x as 1 approaches from the left-hand side, f of x would be negative 1. Negative times 1 squared would be a negative 1. And the same thing from the positive side. F of x would equal a negative 1 squared, or negative 1. Since these two do not equal each other, that's going to be a removable discontinuity at x equals 1. All right, critical thinking questions. Give an example of a function with discontinuities at x equals 1, x equals 2, and x equals 3. Well, there's actually an infinite number of these, but probably the simplest one might be f of x equals 1 over x minus 1 times x minus 2 times x minus 3, because any one of those would give it a 0 denominator. Of the 6 basic trig functions, which are continuous over all real numbers, which are not, which types of discontinuities are there? Well, if you think about the sine and cosine waves, okay, those would be continuous. But if you think of all the other waves, secant, cosecant, tangent, and cotangent, they all have asymptotes, which would be infinite discontinuities. So if you want to go back and look at your graphs of those, you could see that pretty clearly. Right, and that is where we're going to stop for this in-class worksheet.